So this tutorial is for a problem where we have a box of mass m, okay, and it is attached to two springs. We're going to call this one K1 and we'll call this one K2, all right? And the surface is also rough, so there's a coefficient of friction, right? And this is a problem that I have given one of my classes. And the idea is to figure out how long it takes for the block to come to rest, right, due to the friction. So if the block were not on the rough surface, if this surface were frictionless and this were connected to these two springs and I just pulled the mass back, then the box would just oscillate forever, right? The box would just oscillate forever. And if I wanted to set up Newton's second law, let's look at the y direction first. So if I draw a free body diagram, and let's actually draw a coordinate system here. Okay. If I draw a free body diagram of the box, in the y direction we have mg down, and we have the normal force up, and these cancel out, and therefore we can say that the normal force is equal to the weight as it ought to be on a flat surface. And then in the x direction, we have Hooke's law for both springs. And x, okay, is going to be the same in both cases, because if the block was originally at equilibrium or at x equals 0 with both springs unstretched, then they were both stretched / compressed by the same amount in this process. Okay, so this x is a stretching in one and a compression in the other, but it's the same distance in both cases. And then we want to include friction. Okay, and of course this is equal to ma. Okay, well, so the purpose of this particular problem was to write a computer program that would solve this equation. Okay, and if I rewrite this equation, let's divide, well, so first things first, let's do this. Let's say that max is equal to negative k1 plus k2 times x minus mu mg. Okay, and what we will do is we'll worry about this minus sign here in just a little bit. Okay, but for the moment the minus sign indicates that this is going to be opposite the direction of motion. This minus sign indicates that this is a restorative force. So we're actually going to have to take some great care in assigning what direction the friction force is going to be. Okay, so actually we can even see that from the free body diagram. Technically in this case this should be plus, right? Because I would have the force from spring 1, the force from spring 2, and if this is the direction that if this is the initial direction of motion, then the friction is going to act in the opposite direction of that. Okay, and that's kinetic friction, so we'll give that a K. So this is a crude free body diagram here, but this kind of gives you a sense of what's going on. But I'm going to leave this minus sign here for the moment because we'll see that, well, we'll explain what happens to it when we get to the code. Dividing through by m, and by the way, this is just a new spring constant, so I might as well just call it a new number, call it K3. Okay, so when I divide through by m, here we get this particular equation, and k over 3 represents the angular or the square of the angular frequency divided by the mass. And so to numerically solve this system, we're going to break this up. This is technically, well, let me write it off to the side here. Right? A is equal to both dv dt and d squared x dt squared. Okay. So as far as position goes, this is a second order differential equation. But it's a first order in velocity, right? So usually when solving differential equations, it's advantageous to reduce a second order system down to two first order systems, right? So what we're going to do is we're going to say dv dt is equal to negative k3 over m times x minus our friction, and that dx dt is equal to v. Okay. So here are my two equations that I'm going to use to solve this system. Right. Now, the whole point again is to do this numerically. Okay. The whole point is to do this numerically. So what we're going to do is we're going to approximate our equations by deltas. Okay, and so what this is going to do, what I'm going to do at this point is I'm going to let delta V represent Vj plus 1 minus Vj. Okay, and delta X is going to be Xj plus 1 minus Xj. Okay, so here J is an index. Oof, that's terrible. Right. J is an index. And so what this system is going to do, if I insert this into my delta V, and I insert this in for delta X, right, what we're going to get would be Vj plus 1 minus Vj over delta T is equal to negative K3 over M times X minus mu G. And so what this equation is saying is if I have some given velocity Vj, so the Vj represents a given initial velocity. And Vj is going to be the updated velocity. So J is an index that says if J is equal to 1, then that is the velocity at my index 1, and I'm calculating the velocity at index 2 with the Vj plus 1. And likewise, xj plus 1 is going to be the second index of position minus the first index of position. So this is just two positions, the difference of two positions. And the difference of two positions divided by time is, of course, equal to velocity. Okay, or at least average velocity. So the whole point here is to take a dt or a delta t that is small, such that this average velocity approximates your instantaneous velocity over the motion of your object between these 2 points. Okay, that's the, this is a non-trivial thing numerically, but that's the goal. Okay. So if I solve this system of equations for Vj plus 1 and Xj plus 1, I'm going to get minus K3 over m times x plus mu g times delta t plus Vj, and xj is going to equal v dt plus xi. So, or I'm sorry, xj. So, and this should be xj plus 1. Okay. Now the question is what to do about this x and what to do about this v. Well, I can't compute xj plus 1 until I've computed my velocity. So this has to be j, okay? So this is your jth velocity. So if j starts from 0, then j equals 0 would be my initial conditions. So whatever my initial values are for t, x, and v, those are going to be my j equals 0 indice values. Okay. Now, the Euler-Kromer method that we are going to use, Euler's method is really, really stable over first-order differential equations, but second-order differential equations, it can have instabilities grow rather rapidly. So to overcome that, what we do is we use the initial x position and the initial velocity value to calculate the next velocity value, and then it is this velocity value that we use down here. Okay, instead of just using VI or VJ rather, we would use VJ plus 1. All right, and actually let me clean that up a little bit. So now that we have the updated velocity value, I can multiply that by my time interval and add my initial x value, and then I can get my next updated x value. Okay, so that is the idea here, right? And this is what we're going to program in Python. Okay, so stand by. So now that we have the system set up, right, what we're going to do is show a numerical algorithm that will allow us to calculate the uh, motion of the cart, right? That is the goal here. So first things first, the code as written, okay, um, begin by importing all of your necessary libraries. In this case, we only need um, NumPy and Matplotlib. And the next thing to do is to define our time. Now, here's the thing, okay? With this particular problem, this is going to be a little bit of guesswork on the time interval. So this is just a generic guess, okay? We're just going to say, okay, I'm going to let my system go from 0 to 5 seconds, and we'll see what happens. N here is the number of steps that the calculation will take. Technically, 1 minus this because we're already going to have initial conditions, and so I only need to find 1 minus this minus 1 calculations. And my time interval that we specified, so there could be some play with these two parameters based on the data. If the data don't look really clean, then it could be that we didn't pick a good step size. And if the system really doesn't behave weirdly, then we probably didn't pick a big enough time interval. Okay. So we've defined our constants. The first spring constant was 50 newtons per meter. The second spring constant was 100 newtons per meter. And the way this particular problem works out, the spring constants just add. Okay. The mass of the cart was 0.5 kilograms, and the coefficient of friction is 0.3, and gravity is 9.8. Okay. So then we define our x and v arrays, our position and velocity arrays, and our initial position for the cart is going to be pulled 15 centimeters or 0.15 meters in the positive x direction. Okay. Now, so here is the velocity equation for the Euler-Kromer method, right? And by the way, so it's this right here that differentiates the Euler method from the Euler-Kromer method. And it's this right here that makes the Euler-Kromer method a little bit more stable. Okay, so just be aware of that. But this is the result of the calculation, except I haven't included the frictional term yet. Okay, so we haven't included the frictional term. And oftentimes it's advantageous to do this just to make sure that your code is going to give you something that works, right? You want something that will work. And so what we want to do is test our code, and then the position is updated like this, okay? And so to start, we're just going to plot our times and velocities, okay? And so if I run this code, this is what we get. All right, okay, great. So we have oscillations, we have sinusoids. This is great. Without really knowing what the frequency is based on the K values and the mass and things like that, it might not be, immediately apparent that we have the correct solution, but for the moment, let's assume this is the exact solution that we're looking for in the non-friction case. Okay. Now, one thing to note, all right, that our velocity starts at 0 and then becomes negative, and if that should make sense, right? Because the cart is going to start with the spring is going to be pulling the cart back toward equilibrium. And if I displace the cart in the plus x direction, then the springs are going to be pulling and pushing that cart in the negative x direction. And so its speed will be in the negative x direction initially. Okay. And the speed is maximized when the cart goes through the equilibrium position. Okay. And then the speed is 0 when the cart reaches the furthest point in the negative x-axis, right? And that's where it turns around. But when it turns around, the speed has to be 0. And then the springs start pulling and pushing in the positive x direction, and until it's maximized as it goes through the equilibrium point, and then it goes back to 0 at the end point. So the velocity and the position should be out of phase by 90 degrees. And let's see if that's what we get. So I'm going to plot these on the same plot. This is not always advantageous to do, but for the moment, this will tell us something. Okay. All right. So, number one, the amplitude of the displacement relative to the speeds is very small, but you can see what we're talking about here, right? So my position starts at, and as a matter of fact, let's just take a few cycles here. So my object starts at about, well, it starts at 0.15. I can get my cursor right there. Maximized right when the velocity is 0, and then the velocity is 0 once again when the cart is minimized. Okay. And well, so the basic idea is that the position is 0 when the velocity is maximized, and the position is maximized when the velocity is 0. That is the take-home lesson here. Okay, and any slight deviations from that are slight numerical instabilities, but overall the shape is pretty solid. Okay, so we'll just work with this and assume that this is good enough. Okay, so here's the kicker. Okay, here's the kicker. I want to include my friction, and it's going to be minus, but the minus is out front, so this is going to be plus mu times g. Okay. Nothing really changed. Okay. Nothing really changed. This is an offset term. The solution to the exact differential equation for position is indeed sinusoidal if you just leave mu naught times g as a negative term in Newton's second law. Okay, and so it is just an offset term, but the acceleration that it's causing relative to the strength of the springs is very small. So not only is it an offset term and not an actual damping term, but it's not really visible on these graphs compared to what we just saw, right? So we really don't notice anything. So the crux is that we need to make mu times mg, we need this friction term to always be acting against the direction of our velocity. So we need to multiply this by the sine of the velocity and then take the negative of that. Okay, so how do we get the sine of our velocity? Well, one way to do it, okay, one way to do it is going to be, well, let's just pick a velocity term or a velocity point here. So let's just pick velocity at the 40th index. Okay, so the velocity there is negative 1.68955. All right, essentially negative 1.7 meters per second squared, or negative 1.69. So I want to get just the sine of that. Okay, so one way to do this, okay, is to take that value and divide it by its norm or its absolute value. Now, one way to get an absolute value in Python is to square a number and then take the square root. Okay, so there we go. That's negative, okay? And that allows us to calculate the sine on the velocity, okay? So what I'm going to do is I'm going to create a test, okay? I'm going to create a test that says for each velocity, figure out the sine, and then I'm going to multiply mu times g times the negative of that value, okay? So would that be, well, so what we're going to do is actually we're going to multiply it by the sign, and then the negative sign out here will either act to cancel that sign out or not. Okay, so I'm not going to adjust any of the signs in here. I'm going to let this negative sign out here do the grunt work. But here's what we're going to do. I'm going to define a new variable, and I'm going to say Vs for the sine on my velocity is going to be equal to Vi divided by the square root of Vi quantity squared. Okay? And then I'm going to multiply my mu naught g, or mu g, times this value. So if Vs is positive, then mu g Vs is going to be negative by virtue of this sign out front. And if Vs is negative, then this term will be positive as a result of that. Okay, so now let's see what happens. Uh-oh, we got an error. Okay, so invalid value encountered in the double scalar. So what this error is telling you is that there's a value in here that is not going to work. And this should not be a surprise, because if I comment this out and take this away, okay, and this is basically the code we just had, so this will run, and lo and behold, what this is saying is, okay, there's some of my velocity points are 0. And here I'm dividing by those velocity points. So I can't divide by 0. So here's a not terribly elegant method, but a brute force method that will do the job. Okay, so what we're going to do is we're going to make an if statement. If, and we're going to test something. So if vi is not equal to 0, and not equal is a exclamation point and an equal sign. So this is saying if v not is not equal to 0, then I want to calculate vs as I just did. Okay? And my second statement is going to be if vi equals 0, then vs equals 0 as well. So now this is saying as long as it's not equal to 0, then this calculation should be valid. And if it is equal to 0, then just set it equal to 0 because the velocity is not moving anyway. This term will go away at those points anyway, right? So with that in mind, there we go. Now let's see what happens. Okay, so there's multiple plots on here. We'll clear that out and we'll run the code again. All right, so now we can clearly see that this is decaying, which is the behavior that we're expecting, right? And so at this point right here, now if we kind of blow this up, we can see that some really weird things are happening, okay? But these are numerical instabilities as opposed to actual physical phenomena. We can claim with relative ease that the mass would stop oscillating right around in here. Okay, and if you want to prove that to yourself, you can even change these values. Okay. And it kind of helps it die out a little bit, right? And it makes the point here a little bit more apparent. So one other thing to note, let's actually comment this out. And this is what we get here. So this is just the velocity, all right? This is just the velocity. Pretty interesting plot, right? So the motion effectively stops somewhere right in here, okay? And what happens if we just let at those turning points where the velocity is 0, the sign on Vs to be 1? Let's see what happens here, right? There's effectively no change, okay? There's effectively no change. So what that's telling you is that we've picked our signs appropriately, okay? That's what that's telling. And so I hope that this is a bit of a slick way of getting around the problem of what direction your friction force is traveling. If you write code that will do air resistance, for example, especially if you're working in 2 dimensions, if you're doing a projectile in 2 dimensions, you need to be able to make sure that your air drag is opposite the direction of your net velocity, right? And you would do something similar to this to do it. You generally don't have zero velocity in air resistance, but you would do a procedure similar to this, but you would do it in 2 dimensions to make sure that your drag force is in the opposite direction that your object is moving in. Okay. So this is how you solve the problem of an object with, well, a box with 2 springs and friction involved. Okay. So that is the solution to the code, and I hope that this was helpful, and we will talk to you in the next video.